Welcome everybody to tonight's presentation on heat pumps. Of course, this is the MAREA, the Mid-Atlantic Renewable Energy Association. We are a nonprofit, all-volunteer association dedicated to education on renewable energy and sustainable living. Of course, tonight we have our presentation on heat pumps, but coming up in February, we have PA Fiber Shed. PA Fiber Shed will provide an in-depth look at Pennsylvania's fiber and textile economy. And if you don't live in Pennsylvania, it doesn't matter. It's relevant anywhere. Um, we'll learn what it will take to revitalize fiber and textile production across the U.S., including policies and initiatives that can support the effort and the practical steps individuals can take to help reduce emission. Well, I'll just back up. It's going to highlight the benefits of natural fibers and local production of textiles. I think it'll be very interesting. And then in March, we have a presentation. We'll give you a little more information on it soon, but presentation on recycling. And then in May, we have an update on the EV charging installation of infrastructure. A lot of exciting things are happening there, and I think you'll find it interesting to learn what's been happening there and what's actually in the works. There's a lot in the works when it comes to EV charging. Final note, we're looking for new board members. It's not a lot of work, but you do get to work with a lot of great people. So if you're interested in that or helping in some other way, please contact us at our email. We'll put it up on the chat, but it's themarea, THEMAREA at gmail.com. And now Phil will.
No, at Gmail. Okay. That's for the Gmail.
Yeah.
Sorry.
So Phil will now introduce our speaker.
Yes, tonight we're presenting Not Your Father's Heat Pump. And I'm pleased to introduce tonight's speaker, Robb Aldrich. Robb is a principal mechanical engineer at Stephen Winter Associates. He has been with the firm since the year 2000. Robb focuses on building energy systems, researching new technologies, monitoring performance of systems, and working with stakeholders across the country to better, healthier, more efficient buildings. Since 2010, his focus has shifted more and more towards heat pump technologies and electrification of residential buildings. Evaluation and research into new technologies and systems have been a key part of Robb's work. These efforts, often funded by government agencies, utilities, or other stakeholders, have led to much deeper understanding of system performance and integration. This allows for a more holistic approach when consulting with clients on specific buildings. Research and evaluation efforts have included energy and indoor air quality implications of ventilation systems, simplified heating and cooling in low-load homes, inverter-driven air source heat pump performance, especially in cold climates, assessment of hundreds of solar electric and solar thermal systems, and performance of heat pump water heaters. Robb has published and presented results of these efforts at conferences across the country. He also leads classes and workshops to help builders, designers, and contractors find effective, practical ways of making healthier, more efficient, and more durable buildings. Welcome, Robb. We look forward to your presentation. Thank you for joining us.
Awesome. Thank you very much. That's quite an intro, although I probably sent it to you. I've never had anybody read it out to me. Let's see if I can advance my slides. I can. Cool. Very quickly, a very little bit about our company, Stephen Winter Associates. We are, the company is pretty much exactly as old as I am, 53 years. We have offices in Boston. I'm in our Connecticut office right now, Manhattan and Washington, D.C. And we're mostly architects and engineers. We don't do a lot of conventional design. We do a lot of research, evaluation, consulting with all kinds of agencies, as well as builders, developers, property owners, really looking to make buildings better in lots of different ways. My focus has always been on residential buildings, single family and multifamily both. And as that kind of bio mentioned, heat pumps and electrification are front and center in almost everything that we do. I'm going to get into hopefully it's the right level of detail for the audience. It's a little bit technical. It's really focused on how to get good heat pump installations. Maybe it's too much in the weeds for some people, maybe not enough for other people, but certainly happy to dig into more detail at the end when we start some discussion and questions.
Hey, Rob, if it helps,
Yes.
just my own personal experience, I have a heat pump. It doesn't work below 35 degrees.
All right.
And my heat pump guy says I can't put anything in any better. So I have to use an oil furnace when it gets cold. So I'm very
Yeah.
interested in the weeds, but
Well, I think you might need to talk to a different heat pump guy, quite
yeah,
frankly.
okay.
Um, the heat pumps that I'm going to be talking about specifically are people may have heard the term inverter air source heat pumps. That's what ASHP stands for, air source heat pumps. It extracts heat from the air to heat the home. The inverter is really inverter-driven compressors, which allow the compressors to be variable speed. That and some other design features really have allowed heat pumps to operate much better at much colder temperatures. Old school heat pumps, decades ago, very common down south, very common in Florida. They weren't supposed to work below 30 degrees. It rarely went below 30 degrees. And if it did dip below 30 degrees, you would use electric resistance. That's the way heat pumps work. But that has changed dramatically. Those products are still out there for sure, but they're not the products I'm going to be talking about. I'm going to be talking about inverter driven air source heat pumps, many of which can work really well in cold weather, because that absolutely has been a limitation. That's the second bullet here. They can work really well, but we've done quite a bit of research and evaluations. They don't always work well. You really have to do it right. They have to be designed well, installed well, operated and maintained well, and that's really what I'm going to be talking about. If you don't do it right, poor efficiency, poor comfort, leaking refrigerant, which has all kinds of uh, negative climate implications. Here's an outline of the kind of what I'm going to talk about. 6 steps. Be clear about the goals when you're installing a heat pump. Consider building efficiency. Calculate design loads, and then designing the system. Go through ducted and ductless systems, single zone versus multi-zone systems, properly sizing equipment, and also a little bit about humidity control. I'll talk a little bit about good installation, and then I'll end with talking about operation and maintenance. So be clear about goals. I think I only have one slide for this section, and it really is, programs and incentives in the Northeast, where I work mostly, are pushing heat pumps and electrification as fast as possible, and many times too fast, in my opinion, to really get good installations. But I encourage whoever is thinking about heat pumps just to be clear about why you're installing them. Are you installing them to reduce CO2 emissions? Certainly valid. Are you really focused on comfort? More heating, more cooling, both? Cost is almost always a big picture for whoever it is installing these. Upfront cost, operating cost. Sometimes health and safety are big drivers, getting rid of on-site combustion and any risks associated with on-site combustion. And one that used to be front and center, but maybe is a little more in the background, is self-sufficiency. It used to be some of the heat pump early adopters really wanted to go all electric. They had a PV system, their heating and cooling was all electric, and they didn't need to, you know, they were zero net energy. They didn't owe the utility anything at the end of the year. All of these can be valid. I just encourage people to be clear about what they're looking for when they are going about installing a heat pump. That went in the wrong way. Oops, sorry. I'm not sure what happened. Share again. You see my screen?
Yes, it's back.
Okay, sorry for that hiccup. The second thing I want to talk about is to consider the building efficiency. Consider how efficient the home is if we're talking about a single family home or any kind of building. There are several reasons why these heat pumps work better when the heating and cooling loads are lower, especially heating loads, because that's been the limitation historically. One of the first reasons is just upfront cost. So if you have a home that needs 40,000 BTUs an hour on the coldest day versus 20,000 BTUs an hour, the cost of the heat pump to meet that load is going to be considerably more expensive. And certainly boilers and furnaces get more expensive as they go up in capacity, but they don't get as expensive as fast. And frankly, the smallest furnaces you can get are usually 60,000 BTUs an hour. So there's really a lot of leeway. We see that people who try to electrify their homes without paying attention to efficiency at all, just the capacity of heat pumps they need is really high, and that gets really expensive. Upfront cost, one of the reasons to consider efficiency. The second is comfort. And there are a few things about comfort. One is heat pumps provide air during the winter at cooler temperatures than a furnace would. A furnace might provide, hot air 130 to 160 degrees Fahrenheit, where heat pumps are down in the 90 to 120 degree range. This can cause comfort implications. If you have very drafty, leaky windows, you may not be comfortable with 100-degree air blowing through the room. That may exacerbate drafts, where 140-degree air from the furnace, that might have been okay. So this is something that it actually works both ways. I've heard other people install heat pumps say, God, the furnace blasts on at 150 and then it turns off, and then it blasts on at 150 again and then it turns off. Whereas the heat pump is nice and steady at 100 degrees Fahrenheit. That can be more comfortable. But regardless, with the lower air temperatures, comfort is more of a concern, and doing air sealing, insulating a building can help with comfort implications, regardless of how you heat. But those problems can be more pronounced with a heat pump where you have lower supply temperatures. Another potential reason to consider loads is because of duct size. And Phil, you or somebody asked kind of explicitly about this when you're talking to me about setting up this talk. If you had an existing home that you were thinking of electrifying, and you have a register that provides 60 CFM, cubic feet per minute, if you have a furnace that's providing 150 degree air, 60 CFM will give you about 4,800 BTUs an hour of heat. If you only have 120-degree air, you're going to get only 3,000 BTUs an hour of heat with that same flow rate. You'd have to do a decent load calculations and assessment to see if that 3,000 BTUs an hour would be adequate for the space you're trying to heat. It might be fine. If it's not fine, insulation, air sealing, weatherization to reduce the loads can allow you to reuse more of the same duct system with a heat pump that you may have used with the furnace to deliver an adequate amount of comfort. The other thing is operating costs, and this is a tricky one because in a lot of the territory that I work in, natural gas prices are lower than electricity. Heating with natural gas is less expensive than heating with electricity. Certainly not always the case. Prices vary, even across a small region. Fuel prices vary substantially. What we found is this is especially true in new construction. If you build a new efficient home, even just a code compliant home, going all electric, eliminating any on-site fossil fuels really can save energy. Yes, the operating cost of a heat pump might be higher than a gas system would have been, just paying for the fuel. But if you avoid any of the infrastructure to install gas or oil tanks or propane tanks or whatever, and if you have natural gas, if you avoid the monthly meter fees, I pay I think it's between 16 or $18 a month for natural gas at my house. I still use gas. Um, but this can be this can really be improve the bottom line. If you have an efficient building, heating with a good heat pump installation can still be competitive, even if gas rates are, less on the surface. But it really, really varies. The third thing I want to talk about, and this is something that's, gosh, really challenging in our work, is calculating design loads accurately enough. And design loads are basically the peak loads. What's the most cooling, the highest level of cooling, the highest level of heating that a home or a space is going to need, and then that's a key factor in how you select equipment, how you design equipment. I think I do recommend that people use really good procedures. Manual J, ACCA Manual J is touted as the standard, and it's certainly a good method. I use methods from ASHRAE Fundamentals, their residential load factor method. If somebody is very geeky, there are other, hourly models that are certainly good to predict loads, but doing good procedures, using sound procedures is the first step. And what we see again and again and again from designers, mechanical engineers, designers, contractors, is they're just very, very conservative. They don't want to be caught short by designing and installing a system that doesn't have enough capacity. So they hedge and they fudge. And it's really common for us to see systems that are 2 to 3 times larger capacity than they need to be. And this has some pretty certainly cost implications, but also efficiency and maybe comfort implications, which I'll talk about. So here's an example. This was actually a new home. This is half of a duplex in a development that we were working on. We were doing ratings on these buildings. The mechanical engineer, the mechanical designer came up with a design heating load, so a peak heating load of 31,900 BTUs an hour. I, as an exercise, reproduced these loads. I did calculations on my own. I came up with 13,700 BTUs an hour. That's a lot different. The mechanical designer's loads were 2.3 times higher, which I would like to say is unusual, but it's not. And it's really easy to see why they're higher. And this is something I really try to drive home with engineers and contractors. If I were to take my base load, 13,700, and I were to, into the model, into the calculations, put the inputs that the designer used. So, for example, we could see what the designer used, code minimum insulation and window performance values. This is an Energy Star home. The values are going to be better than code. And by taking my values and kind of dumbing it down to what the designer put in, my loads went up by 1,400 BTUs an hour. The big one is infiltration. So this designer assumed that the infiltration levels were average for this home. It's kind of a soft, kind of a squishy qualified number. New homes really should be tighter than tight. Tight is also another kind of qualification you can put in. Energy Star homes are really kind of off the scale for tightness, or should be. When I reduce the infiltration from very tight or tight to average, my design loads went up 7,500 BTUs an hour. The designer assumed that ducts were running through the attic and had a 20% loss. All the ducts were going to be within the conditioned envelope of the home. There weren't any ducts outside of the conditioned space. There should be no duct loss. That's another 4,800 BTUs an hour. And finally, the design temperature used. And this I can't quibble with. The site where this was being built, there were 2 weather stations kind of nearby. One showed a design temperature of 16 degrees Fahrenheit. One showed a design temperature of 9 degrees Fahrenheit. I used the 16. I found that that's fine for all the projects in this area. The designer used 9, which I can't quibble with, but it makes a big difference. It's 4,100 BTUs an hour. It makes a big difference in the design loads and the subsequent equipment that you install. So if I put in all the designer's inputs, I came up with 31.5. The designer had 31.9. Very, very close when you put the same inputs in. But it really makes a difference. This project ended up with heat pumps that were, 2 to 3 times bigger than they needed to be, and that has efficiency implications. Here's an example to kind of demonstrate that. This is one of the systems that we monitored. This was actually in Western Massachusetts. This was an old leaky farmhouse, and we monitored the performance over a winter, several winters back. So every dot on this chart is an hour during the winter. And on the x-axis, we have outdoor air temperature. This was in Western Massachusetts. And on the y-axis, we have the heat pump output in BTUs per hour, actually thousands of BTUs per hour. And that purple line is the listed maximum capacity of the heat pump that was installed. So you can see none of these dots come close to what the maximum capacity of the heat pump was as listed by the manufacturer. First thought may be that, God, this heat pump is dramatically underperforming. It is not even coming close to its kind of rated heat output. When I talked to the occupant of the home, no, totally comfortable. They were fine, very comfortable. They thought everything was working great. So when your heat pump output is less than half of what the maximum capacity is, and you're comfortable, that's an implication that your heat pump is much bigger than it needs to be. And that was the case here. This person did not do any load calculations. They picked the biggest heat pump they could and they installed it because bigger is better was the thought process back then. And that's just not the case. I mean, this was one of the first studies actually that found that this is not be the case. This was a 1.5 ton heat pump, so nominally 18,000 BTUs an hour. We found a seasonal COP from this heat pump of 1.6. So COP is kind of like efficiency. It's heat output over electricity input. You can get efficiencies above 100% because you're actually moving the heat. You're not just converting the heat. We'd like to see COPs 2.5 to 3. That's kind of the ideal kind of wintertime COPs for these systems. This was almost half that. But again, very, very oversized. Here is a different home that we monitored. This was actually in Vermont. It was even colder. Same chart. Every dot is an hour. And here we see many, many hours where the output of the heat pump was actually higher than what the maximum capacity was. This home was doing a very deep energy retrofit, pushing passive house levels. It wasn't completed, this deep energy retrofit. So this heat pump actually was undersized. I think it was sized more for the finished product. But when we monitored it, there was still some work to do in the retrofit process, some extra installation and air sealing. But this is the same exact model. We can see the output greatly exceeded what the rated output was for a lot of the time. And the seasonal COP here was 2.4. And again, this is in near Burlington, Vermont. We can see we had heat output down at minus 20 degrees Fahrenheit. Not a lot. Output definitely tails off that at those temperatures, but really decent output, well below zero. And it's definitely possible with the right equipment. This equipment does not cut out at 30 degrees Fahrenheit, for sure, for sure. So to wrap up load calculations, I see it done poorly. I see it glossed over so many times. When these heat pumps first came out, it was, well, they were variable speed, so they can modulate, they can vary their capacity. So, my hope, other people's hope was it doesn't really matter if you oversize them because they're variable speed. All of the evaluation efforts we've done and others have done has shown, yeah, oversizing matters even more than with other types of heat pumps, unfortunately. These systems can only modulate to a point, and if they get to a point where they can't kind of cycle any lower, they start cycling on and off. If they can't turn down any lower, they start cycling on and off, and that really leads to to some performance problems. Actually, I'll go back to this chart. You can see this heat pump, if we look here at the output on the 0 line, let's see, if I click there, you can see, hopefully see my laser pointer. When the heat pump output is 0, the heat pump is turned off. This doesn't happen until we're well into the 30s, high 30s, 40s. If we go to the previous slide, this heat pump cycling on and off all the way down below 0. And that's partly the way that the occupants use the heat pump, but it's also this is so oversized that even if it's running, it's cycling on and off, on and off, on and off. And that's what leads to poor efficiency. One of the things that can lead to poor efficiency. Okay, so talking about design, kind of 4 points I'm going to talk about here: ducted versus ductless, sizing equipment properly, single zone versus multi-zone, and a little bit about humidity control. Sorry, I'm going to grab a drink. So this is my first advice. Try not to put a ductless head in every room. Ductless heat pumps are very popular and they have a lot of fantastic applications. I recommend them a lot, but certainly not in every application. The marketing team for almost every heat pump manufacturer will tell you to put a head in every room, guarantee comfort in every room. It's not accurate. I'll show you what it can lead to. It can lead to oversizing it, to lead to very expensive systems that are not efficient and in extreme conditions not comfortable. I do recommend distribution and comfort. You can't necessarily put one ductless heat pump in a room and expect it to heat the whole home. Certainly understand that, but putting a head everywhere is not usually a solution. You still need to consider distribution, whether it be a ducted system, a combination of ductless and ducted, and definitely do match heat pump capacity at design temperatures to design loads. Bringing it back to those loads again. Don't oversize equipment to get good performance. I'm going to mainly walk through an example here. This is a home, some colleagues, some friends of mine, they bought this home, did a gut rehab. They did actually a wonderful job. Basically got the home up to code levels, really. Even the air tightness, they did a great job getting it airtight. So really performance-wise, this is pretty similar to kind of a new single-family home, even though it was a rehab. I'll show you a quick picture of the systems that they put in. On the left is you can see a ductless head. This is kind of in the walkout basement section. It was going to be a spare bedroom, but it is turned into a home office during COVID. And on the right, you can see a small ducted heat pump. I think the photographer was lying on the floor of the basement looking up. So this is the heat pump that serves the first floor. This is quickly showing the plan. So this is the basement. The shaded sections are the conditioned part of the basement. You can see it's a walkout, and that yellow area has a lot of glass actually. And just here's the load. So the total heating load for the basement, 6,700 BTUs an hour. Total cooling load, 2,800 BTUs an hour. Here's the first floor. Total design heating load on the first floor is 14,000 BTUs an hour. The heating load and the cooling loads were often pretty well matched, not in the basement. Basements are kind of different. The heating loads dominated a little bit, but they were close, the heating and the cooling loads. And here's the top floor, the second floor, where all the bedrooms are. And you can take a look at some of the loads in the bedrooms. The design heating and cooling loads are, in the orange room here, less than 2,000 BTUs an hour. In kind of the primary bedroom, 2,500. If you add the walk-in closet, it goes up a little bit, and that's kind of a big walk-in closet with some windows. But, well, we'll talk about how to size, how I would size systems for this home. One thing I wanted to, this is a text from an application note from a heat pump manufacturer, major heat pump manufacturer. I have a link to the note down here. Their advice is if an indoor unit nominal capacity is more than 50% higher than the maximum heating or cooling load in a space, humidity, overheating, and higher than expected system energy usage can occur. And I was thrilled when this manufacturer published this note because this is what I've been kind of harping on for a long time. Now I have some manufacturer documentation to back it up. I'm going to go back to the bedroom here. Here's this green bedroom is kind of typical. The heating load is 2,600, cooling load is 2,200 BTUs an hour. The smallest ductless heads that you can get have ratings of sometimes 9,000 BTUs an hour, sometimes 6,000 BTUs an hour. These are dramatically oversized for these bedroom loads of less than 3,000 BTUs an hour. So it's not possible to find a ductless head that fits these bedrooms while still complying with this manufacturer guidance. This manufacturer's marketing department will tell you, no, 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 put a head in every room. It's great for sales. But really for comfort and efficiency, it's not a great practice. So what this homeowner did on my recommendation, or actually I designed the systems for this home. There's a ductless head in the basement, which is kind of an open space. And there's a ducted system serving the first floor and a ducted system serving the second floor. It's a 1-ton system for second floor and the first floor. Every contractor who bid on the job tried to upsell them, install bigger capacity, told them they wouldn't stay comfortable all winter, and they've been in the home for 4 years now, I think. Yeah, this was kind of a COVID renovation, which was interesting. It's been perfectly comfortable, plenty of capacity. We've monitored the performance. There's actually capacity to spare. So aggressive load calculations and good sizing result in comfort and good performance. Now, single zone versus multi-zone. For this home, I strongly recommended that they go with 3 separate systems, 1 system for each floor. And this also rubbed a lot of contractors the wrong way. Why wouldn't you get a 3-zone system? You could have 1 outdoor unit serving all 3 indoor units. You can see 4 outdoor units here. There's a water heater. There's a heat pump water heater. That's one of the outdoor units. But the 3 units that are on the deck do the space conditioning, the heating and cooling. The first data I ever saw on multi-zone performance was from an evaluation that I linked to here, Cadmus did in Massachusetts, in Rhode Island. And I looked at the results from single zone system and multi-zone systems. On the x-axis here, we have the system configuration. So 1-to-1 means that there's 1 indoor unit and 1 outdoor unit, single zone. 2-to-1 means that there's 2 indoor units off of 1 outdoor unit. 3-to-1 is 3 indoor units off of 1 outdoor unit. And this study found that there was just a steady decline in efficiency as you went from single zone to more multi-zone systems. I was baffled at this. I was surprised. I couldn't understand why this trend would happen. But this came out a decade ago, and I think we have a better understanding, I think, of why this trend occurs. What we found and what I've shown is, oversized air source heat pumps are less efficient. Oversized multi-zone heat pumps can be much less efficient. And this is because, well, I'm not sure, I maybe won't get into all of the physics of the operation of the heat pumps themselves, some of which I don't fully understand. It's better left to the manufacturers. But multi-zone systems can't modulate over as wide a range, basically, is one of the key factors as single zone systems. And that's one of the reasons we believe that the multi-zone systems are less efficient, can be less efficient if they're not in the right application. This is some text from that same application note from the same manufacturer. The outdoor unit should not be selected based on how many indoor units are desired. If the outdoor unit is oversized just to provide a certain number of indoor units, overheating, humidity issues, and higher than expected energy usage can occur. And this can be, there can be some dramatic problems on efficiency and comfort when people oversize their systems just to get ahead in every room. And here's an example. This is a made-up example. There are real examples, but nobody wants me to talk about them. There's threats of lawsuits, etc. But this is a hypothetical. So this is a home, and I have 5 spaces in this pretend home, and here are the design loads for this home. This could be both heating or cooling. I've shown it as heating because heating is often the driver in retrofitting existing homes anyways. So if you add up all the design loads from this house, you get 20,000 BTUs an hour. Now, if we look at what equipment might be available to serve that load, if you wanted 5 zones, a 1 or 2 ton air source heat pump can probably meet the load of 20,000 BTUs an hour. But if you use a 1.5 or 2 ton heat pump, you probably can't get more than 2 zones from that. The higher capacity equipment serves multiple zones, serves more zones. If you wanted to get 5 zones, you probably would need to go up to a 3 or 4 ton heat pump. And basically, that would have twice the capacity at your design temperature than your design load. This would lead to cycling. This could very well lead to overheating certain spaces, overcooling certain spaces in the summer, and much, much less efficiency. So this is the concept of where we see oversizing and overzoning really going wrong. And it can be, sometimes it's subtle. Sometimes people don't notice. Sometimes people say, I thought I'd save more on my electric bill. But in extreme cases, it can be very pronounced, and lawyers get involved, and yada yada. So I recommend single zone systems over multi-zone systems whenever I can, for reasons. It's generally more efficient. If depending on the application, it's usually more efficient. It can result in better comfort. Redundancy is another one. That's the fourth bullet there. If you have a multi-zone system heating your entire house and the system goes down, you don't have any heat, you don't have any cooling. If you have 3 separate systems and one goes down, you still have heating and cooling in the other 2 sections of the house. So it's less urgency, less of a catastrophe if the system goes down. The cost bullet, I have an asterisk because that's one of the first questions people ask. Look, isn't the multi-zone system a lot less expensive? And the answer is usually it's a little less expensive. I see the cost savings I see from going from, say, a 3-zone system to 3 single zone system is between 0 to 10%. Totally can vary depending on the application, depending on the contractor and what they like to install. But the premium to go to multiple single zone systems is usually not huge. And single zone systems might be able to do better humidity control, and I'll talk about that in the next slide. Now, all that said, it's not always possible to go with single zone systems. Sometimes you just don't have room for multiple outdoor units. We see that a lot in multifamily buildings where space to mount outdoor units is really at a premium on the roof or on the ground or mounted on the side of the buildings. And if you're retrofitting a home where, say, it's like a split level home that doesn't have a duct system, it may not be possible to really practically fit a duct system into a home like that. So multi-zone may be one of the only practical systems to choose. But I do recommend if you do go multi-zone, really be careful about sizing. I definitely recommend not oversizing multi-zone systems because that can lead to problems. Now on the humidity control piece, a lot of people install heat pumps wanting to meet three things: heating needs, cooling needs, and dehumidification. It's pretty straightforward to get two of these three. It's not necessarily straightforward to get all three. People might be familiar with ACCA Manual S. This is kind of an equipment selection manual. ACCA is the Air Conditioning Contractors of America? Air Conditioning Contractors of America? I think that's what it stands for. I forget what it, sorry, these are my acronyms. Um, and their conventional guideline, you'll see codes and regulations. We do a fair bit of work in DC. There are regulations that require sizing systems based on Manual S. And the old school kind of Manual S standard, this was going back 40 years or something, was you select heat pumps based on the cooling loads. And it used to be that heat pumps, that's what they were for, is they were primarily for the cooling load. Heating was kind of a secondary bonus. And if you needed a little extra heating, if it got really cold below 30 degrees in Florida, then you had some resistance to provide with the other heating you need. And that's what Manual S told you to do. Select the heat pumps based on cooling. And if you don't oversize on cooling, you can get better humidity control. So when you size an air conditioner or a heat pump to meet your cooling load, to just meet your cooling load, that can lead to better humidity control. If you oversize an air conditioner, it'll cycle on and off, and it won't be on long enough to really wring a lot of moisture out of the air. That's why oversizing air conditioning or oversizing heat pumps for cooling loads can lead to not as good humidity control. So if Manual S says if you can't meet your heating loads with that heat pump sized for cooling, use something else to meet that heating load. Conventionally, it's resistance. It could be a fuel-fired system. It could be a furnace or a boiler. It could be a wood stove or pellet stove, or it even could be another heat pump. And this is what some of the manufacturers are proposing as a way to comply with Manual S, get better humidity control. If you install two single heat pumps, this is what I mentioned, the one-to-one systems might be able to do better humidity control. One can be sized to more for the cooling load and do humidity control, and then one will kick in more often in the winter to supplement the heating. I haven't seen great data on that. I think the concept has some merit, but I haven't done any research. I have not seen any research by others to really kind of vet out better humidity control from multiple one-to-one heat pumps. Now, the strategy that I generally recommend, and the latest version of Manual S is kind of getting into that. If your heating loads dominate, if you're in a cold climate or you have an older building and you want to meet all your heating loads with a heat pump, select a heat pump to meet the heating load. Then if the heat pump is oversized for cooling, use a separate device to manage your humidity. Install a dehumidifier to manage humidity. And this is really the option that I prefer and I recommend because frankly, I don't trust these variable speed heat pumps to really manage humidity under a wide range of conditions. So I would, if you're really concerned about humidity control and really interested in indoor air quality, separate humidity control is what I often recommend. It's not perfect. I mean, it's hard to find one system that can do all these three things perfectly. The stars kind of have to align, I think. But that's a common recommendation from me is to really try to, if you have humidity issues, manage those separately. All right. Looking at max capacities. This table I threw up there just as an example. When you're selecting, it's numbers that I made up, but when you're selecting equipment, here we have heating data. So your outdoor temperatures would be down on the left. Your indoor temperatures would be on the top. I usually design for 70-degree indoor temperature. And if our design temperature is 12 degrees, this particular made-up heat pump can deliver 16.2 thousand BTUs an hour at 12 degrees outside, and it'll use 2 kilowatts while it's doing it. I put this up here for a lot of people who are digging for heat pump information because it's not necessarily easy to find. Not all manufacturers make this easy to find, but it's important to dig this up or to use the manufacturer's software if it's built into their softwares. It's important to match loads to capacities at the design temperatures to get the best system. Oh, I have a link here to the NEAP database, which actually is a good resource. They have minimum and maximum capacities for a lot of products that they have deemed meet their cold climate criteria. So a quick example. This is kind of a load line. Say our design temperature is 20 degrees Fahrenheit. We've done a load calculation. We found that at 20 degrees Fahrenheit, our load on our building or our one floor in a building or an apartment is 15,000 BTUs an hour. 20 degrees is DC design temperature. Certainly gets a lot colder. And then this line just goes from down to there's zero need for heating when it's 65 degrees outside. This is a kind of a useful construct. It doesn't necessarily mimic the real world conditions, but it's a useful tool when kind of demonstrating how heat pumps are sized. Now, if I were to select a heat pump to meet this load, I might look for a heat pump that looks like this. So this is the maximum heat pump capacity. As it gets colder outside, the capacity goes down because it's harder to extract heat from colder air. That's just the second law of thermodynamics. That's how it works. But this is what I'm looking for, where the maximum heat capacity at the design temperature is just at or above what the calculated design load is. And this is very, very close because I made up these numbers to look like they were close. But this is definitely what I look for. Now, a common question is, what happens when you're below that 20-degree design temperature? It has been below 20 degrees in DC this past month. Then what? I do not recommend oversizing heat pump to meet these conditions. All of our monitoring has shown us that, look, load calculations are conservative. In the real world, our loads are well below this load line. You know, these design loads assume that there are no internal gains in the building, no people generating heat, no fridges running, no lights, certainly no sun coming in the windows. It assumes no internal gains. It doesn't count for any thermal mass. So really, practically, if overnight the temperature dropped to 10 degrees, the heat pump could struggle for a while, but the next morning when the sun comes out, it warms up a little bit. The heat pump would be back in its in its operating range where the capacity exceeds the load, and there likely would not be any noticeable impact on the residents. However, if you were to have a week, polar vortex excursion, you have a week in the single digits, then I think you might run into trouble where this heat pump would not deliver comfort. It would keep everything from freezing, it would be safe, but it would not deliver comfort. In my opinion, that's not a reason to oversize heat pumps. I would recommend for really extreme events, separate heating systems be used, whether it be fuel, whether it be resistance, wood or pellet stoves. In my mind, really covering your butts for extreme events is not a reason to oversize a heat pump. I recommend other methods be used to do that. And frankly, I've had this conversation with a lot of clients who are and friends and clients who I tell them, look, if we get a little polar vortex event and it's in the single digits for a week, this may not cut it. And they say, that's fine. We'll plug in some resistance heaters. And I don't think anybody has had to do that. So it really is kind of an extreme event and not a reason to oversize heat pumps. All right, 10 of 8. I'm going to stop design. I'm going to talk about installation. I'm going to go through installation pretty quickly. It's very, very important. I'm going to touch on some high spots. I don't know if they're HVAC contractors here, which I probably won't get in nearly enough detail to satisfy any contractors, but I'm happy to have answer some questions about it afterwards. So first, if you're using ductless systems or duct dead systems for that matter, think about the location of the indoor units. If you know where people are going to be sitting or hanging out, maybe try not to blow air directly on people. Sometimes that leads to comfort issues, but I gotta say, I think the designers these are getting much better, and I very rarely hear complaints anymore about discomfort coming from ductless heads. But it's something to keep in mind locating the indoor units. So think about aesthetics, think about comfort, and there's some other things you think about. You talk about line sets. Locate the outdoor units. We don't want to see this. Certainly follow manufacturer's instructions, and they always say to install them level, prepare the substrate properly. We don't want to see them rolling down the hill. Make sure it complies with all the clearances specified in the manual. Very often we see vegetation growing into outdoor units, which, even if it's not growing into the outdoor units, when it's installed, plants grow, they can get into the units, and it really can be a hindrance to good operation. You also want to keep the outdoor units above snow height, and this is certainly a concern for part of the Mid-Atlantic. This, I think, was in Vermont, this picture. Not a good installation. Um, Much better installation. There's a bunch of systems on the roof of a multifamily building. They are well above snow height, and it's not just snow. A little clearance for leaves or trash or any debris that might be blowing around it's nice to get them a little bit off the ground. These outdoor units are also blowing away from each other. So you'll see the discharge of this one is coming this way, and this one is blowing that way. So you don't have the discharge from one unit blowing into the intake of the other unit, which is really pretty important, but often overlooked. For instance, in this rooftop, this unit here is blowing into this unit here. So if it's 85 degrees outside and you're trying to cool, this heat pump is dumping heat to 85-degree air. It's blowing out 95-degree air. The neighbor's unit has to try and cool the apartment working with 95-degree air. Easily overlooked, but important kind of installation and configuration detail. These units are well above any snow height, and they also have hats on them to shed water or snow or ice that may be coming from above. If these are not always necessary, they're pretty good practice, and for some regions, it's just these little hats get installed, period. That's how contractors work, and that's not a bad way to go. In my experience, it's not necessary. It's not strictly necessary unless heat pumps are exposed to really excessive water or ice or snow coming from above. So if it's under a drip edge without a gutter, or a gutter that's clogged, frozen, that's an issue where you really do need to prevent that water from getting into the heat pump. I'll also note that these heat pumps are on brackets. Most contractors really prefer mounting them on stands on the ground. These are on brackets. One thing to think about with brackets is vibration dampeners are much more important. Sometimes, especially in frame construction, vibrations from these units will get into the building and cause some discomfort. They're very, very quiet, so you often can barely hear these things operating, but sometimes if the frequency is right, the vibrations can propagate in unpleasant ways. So vibration dampeners are important. One kind of unexpected source of heat pumps, and one that I learned the hard way, was unexpected source of water is from other heat pumps. So this homeowner has rigged up a very elaborate snow and rain shedding system with a piece of scrap plywood on this heat pump. We monitored the bottom heat pump here, and we found this bottom heat pump, it was 20 degrees outside, and this was kicking into defrost in the 20s. This was kicking into defrost every 10 minutes. We couldn't figure out what was going on. Then we realized that when this heat pump's operating, it's removing moisture from the air. It's like the like an air conditioner removes moisture from the indoors in the summer, this cold coil removes moisture from the outdoors in the winter, and that drips down. And if you have excessive water dripping down onto heat pumps below it, that'll get on the coil, that'll freeze, and that heat pump will have to go into defrost a lot more often. So this is the project where I learned it the hard way. This was a multifamily building where there were 4 heat pumps stacked on top of each other, and down at the bottom, it was, there were icicles hanging off of it, and it did not work. The solution here was piping, so they installed kind of pipes from the drains so that the water doesn't drip on the units below. Um, some way to prevent excessive water from getting onto heat pumps is important. When you're running line sets, think about the distance. Plan the route before you start running line sets. That's the refrigerant pipes that connect the indoor units and the outdoor units. Shorter is usually better, almost always better. It's important to measure the total run. It's important to measure vertical distance. There are limits to that. And it's important to document these numbers because that's important for how much refrigerant you'll need to add to the system. I definitely encourage thinking about aesthetics, thinking about direct runs. We have 1, 2, 3, 4 sets of these white tubes that contain the refrigerant lines running across this house. This is in the back of the house that nobody can really see from the street or anywhere, so you have to try to get this shot. I don't think this homeowner minded, but direct routes and aesthetics is certainly something to think about. And also, when you're running lines through envelopes, you really want to seal these penetrations. You want to keep air out, you want to keep water out, and you want to keep pests out. This could be a mouse highway in some situations. Insulation lines should be insulated the entire length of the lines, and any insulation outdoors needs to be protected from UV. This installation was like 7 years old, and you can see this was a 3-zone system. You can see for some reason 2 of the 3 sets of copper lines, the insulation has completely deteriorated when it's out in the sun. The insulation's okay when it's in the tube, when it's in the line hide, but not protected from UV when it's outside. Condensate draining is one of the, especially when contractors first start installing ductless heat pumps, getting the condensate drainage right is a very common failing. I've seen so many instances with water running down the drywall when ductless heat pumps are installed. There's no reason for this. You got to do it right. I mean, well, there are reasons for it. There's no excuse for it. This is actually a friend of mine. He installed this condensate drain that goes droops and droops and droops, and it keeps going onto the right. This took 1.5 years for this tubing to completely fill up with water and for water to start running down his wall. You need steady pitch, steady slope. Plan the condensate, make sure it works. And that's one thing I really recommend contractors do when they start systems up. Test the condensate, dump water in the pan, and make sure it goes where it's supposed to go. Refrigerant leakage is a huge issue in many, many ways. I mean, obviously, it'll reduce the heat pump effectiveness, capacity, efficiency. The refrigerants we use are also extremely potent greenhouse gases, so refrigerants getting out into the atmosphere absolutely have a deleterious effect on global warming and climate change. We want to minimize it as much as possible. So making good flare fittings, doing good brazes if you need to braze, really, really important. Using a torque wrench to tighten your flares to the right torque, very, very, very critical to get good. And this again, new contractors struggle with this. Contractors who've been at it for years find systems that work, and they almost never have failures. It's virtually no failures once you get a system that really works well. Pressure testing. You want to pressure, almost all the installation instructions involve pressurizing your refrigerant system to a high pressure, usually 500 or 600 PSI, leaving it for a period of time, making sure there are no leaks, going around to the joints and spraying it with a leak test solution to make sure no bubbles form. That would indicate a leak. I have a link here to a really good paper on, there was an ASHP journal, and I think it was published somewhere else. A really good paper from a contractor and an engineer about preventing leaks in residential systems. Evacuation, removing all of the air, all of the moisture, getting it down below 500 microns of mercury. Critical to remove everything. All you want in these refrigerant pipes is refrigerant and oil. Follow the instructions for good evacuation. And then charging, adding refrigerant. Almost all these systems have a pre-charge that comes shipped in the heat pumps, and that's good for a certain distance of line set length, certain distance of refrigerant piping. Review all these line set lengths, the pipe diameters, do the math, and do figure out exactly how much charge should be added. And record all these values. Record it in the literature. I like to see it written down on the back of the access panel. So if somebody else comes to service these systems, they know what the charge was and they know what the charge is supposed to be. And then adding refrigerant. This can of refrigerant is on a stump, not on a scale. Refrigerant should be weighed in for these systems, for these inverter-driven systems, not for these variable speed systems. Superheating or subcooling is not the way to check charge. The way to get the right charge is to calculate how much should be added and then weigh that refrigerant in. And then startup. This is too often overlooked in my experience, where a contractor, I see it a lot in new construction, where a contractor is banging through several apartments, they install, and they never turn anything on to test to see if it's working. Turn on the system to see if it's working properly. Operate it in heating mode, operate it in cooling mode, measure the intake and the discharge temperatures, make sure it's working. This is just a really important piece of quality control. And measure flow rates. Inducted systems, check the balancing, make sure your flow rates are where they should be. And write these numbers down. I'm a big fan of quality control. A lot of contractors, a lot of programs have required certain levels of quality control, but a lot of bigger contractors have found really writing down all of these numbers being really, really valuable if these systems run into problems down the road. They can see they can see it was working when they left it. They can see exactly what the charge was. I'm a fan of good documentation of this. And then finally, and fairly quickly, operation and maintenance. If a contractor is installing a heat pump in a homeowner's home, I really like for the contractor to educate the homeowner on how to operate this system. If it's not a personal home, if it's an apartment building, I like to see the building maintenance staff or the building management know how to run the system. I like to see educational info for tenants to know how to operate their system well. The biggest drawback I hear from contractors everywhere, or the biggest problem, is that people do not clean their filters. They do not change their filters. This is certainly important to do regularly. Something homeowners can't do that contractors may need to do from time to time is clean blowers and clean the coils and clean blower wheels. These can get kind of gross, especially in humid climates where these coils are wet for a lot of the year. Clean out traps, make sure water drains in that condensate line, and check, outdoor units also. Check the refrigerant piping, repair refrigerant piping, clean the outdoor coils as well periodically. Definitely leads to better performance. And that, I think, is it. Here is that list again of everything I kind of went through. Hopefully it was interesting, useful. And I think if people are gluttons for punishment and want to dig into this a lot more, we have a course on our SWAT Academy where we host a lot of training. We have a 5 to 6 hour course of 70 plus very short videos digging into specific topics, specific examples, some of which I ran through here. But that is it. I'm happy to take questions, discussion, take a drink.
Thanks, Rob.
Joe,
Appreciate
do
it.
you want to go through the questions?
Sure. Just one comment to begin. Someone notes that their only heat is a heat pump, and I live in Pennsylvania, so we just went through all those cold days with absolutely no problems.
Absolutely, yeah.
Second comment was a non-technical question. If I may, why does it seem all these heat pump outdoor units look the same and are so darned ugly?
Um, a lot of the manufacturers, uh, yeah, a lot of them do look the same. So the conventional air conditioner and the conventional heat pumps from like 30 years ago or whatever, are kind of top discharge. They sit on the ground, usually in Florida, and they take air in from the sides and blow the air up. Um, when the Asian products started coming in more and more in 20 years ago, maybe, um, they were all side discharge. So side intake and side discharge. I think that from a practical standpoint, in cold climates, it's a lot easier to protect those side discharge units from snow. Uh, there are wind baffles you can put on those to protect, but if you have heavy snow coming straight down into an outdoor unit, I think protecting that from heavy snow can be a little more involved than with the side discharge. That's my hunch as to why they're all side discharge. Yeah, but you're right. They do all look very similar. They're kind of a beige color. I don't find them offensive, but it's all in the eye of the beholder. So I'm not sure what to say about that.
Next comment pertains to the slide where you were showing furnace temps versus heat pump temps. It's my understanding why heat pumps don't really work for old homes with big cast iron radiators, unless one is willing to rip them all out and start over, which is very expensive. And a similar problem with geothermal heat pumps.
So I was talking about pretty exclusively about heat pumps that deliver forced air. So air source heat pumps where it extracts heat from outdoor air and then it blows warm air into the home, either directly in a ductless system or through a ducted system. There are products that are air to water heat pumps and ground to water heat pumps where it'll extract, products can extract heat from the outdoor air, use that heat to heat water, the heat pump, and then run that water through some heat emitters. But you do run into similar challenges with temperature. Um, that water is usually fairly modest temperature, 120, 130, maybe. I'm not terribly familiar with those products, but I'd be surprised if they're substantially above that in the middle of systems, or old oil boilers. They're designed to work with 180 degree water. So if you have 180 degree water running through a radiator, that's going to put out a lot more heat than 120-degree water, a lot more heat. And yeah, unless you reduce the load of the house, that may not cut it. You may need to replace the radiators with emitters that are more suitable for lower temperature and probably still reduce the loads. Um, there are options, but it's not necessarily straightforward to make use of old heat emitters with a heat pump system. Can be done, but I agree it's not necessarily straightforward. It's not probably a satisfying answer, but
Next comment or question is I have a ground source heat pump. It's a geothermal system that's about 15 years old, starting to have issues with it, and I was told I should plan to replace it in the next 2 years. Any recommendations on a good brand of heat pump? The one I have, Econar, ECONAR, is no longer in business, so getting parts to repair it is a problem.
I gotta say, there aren't any, I'm not terribly familiar with ground source. I'm much more familiar with air source heat pumps. But in both, my experience is that there aren't any kind of products that I would necessarily recommend against or for. I am much, I've, I've had, I've had good experience with lots of different products as long as they're designed and installed and operated and maintained well. I very often defer to contractors, um, because if contractors are familiar with the product, they know how to install it, they know how to maintain it, they have good availability, they can get parts, they have a good relationship from somebody to give them support. Those are huge reasons, in my opinion, to go with specific products that the contractor recommends. Then the question is, how do you find a good contractor? That I'm less able to speak about in a lot of the country. Uh, I'm not sure what to say about that. Um, Longevity is a question, though. Rule of thumb, ground source heat pumps, I say 20 to 25-year typical lifespan. Air source heat pumps, the products that I've been talking about, more like 15-year lifespan. And that rubs a lot of people the wrong way, and I think understandably so. You could take out a boiler that'll last 40, 50 years and replace it with something that'll last 15, can leave a bad taste in people's mouths, understandably. But they still can work really well. And if you're going to have cooling anyways, you probably have to replace your AC every 15 years anyways.
And you spoke to the next question a bit already. Is it possible to utilize a heat pump in a hot water delivery system?
Yeah. It's more challenging. I'm not terribly familiar with those systems. But there's a lot of interest in it. The challenge is that the water temperatures you get from air to water heat pumps, or ground source heat pumps, that from groundwater to heating water, the water temperatures are cooler, usually considerably cooler than what you would get from a boiler. So you'd have to, you know, even more attention to building efficiency, and maybe upgrading or replacing the heat emitters that'll work with those water temperatures.
Next question. Heat pumps seem to have less durability over my 35-year experience replacing two of them. Is there a longevity increase with this retrofit, please, that you were showing?
So, sorry, the last part of that, is there a longevity
Longevity
increase?
increase with this retrofit.
No, I still think that 15 years life expectancy is about right for these air-to-air heat pumps. And manufacturers don't really quibble with that either. So yeah, it is what it is, but they don't last as long as a boiler would last,
Next,
usually.
next is I heat and cool my passive house with 9K BTU Mitsubishi ductless mini splits. One's dedicated for heating, one's dedicated for cooling. One of the units failed within 5 years due to a coil leak. I now do my own service and installation. My complaint is the lack of built-in monitoring or performance or of performance. So the homeowner needs to notice when the unit is starting to perform poorly, often when it fails entirely. Do you see any brands that do a better job of this?
No is the short answer. A silver lining to that is I'm hearing a lot more chatter about it. Um, that's a recurring it's a recurring issue. Yeah, I mean it's possible to not, especially if you have a leak, it can slowly get worse and worse and worse. Um, God, I'm trying to think of the company that I most recently heard about kind of doing some upgrades. But shorter answer is no, but hopefully stay tuned. I have heard a lot more chatter about this. You're not certainly not the only person frustrated by this. Um, Better devices, better instrumentation, quote, smarter systems that can let people diagnose problems more proactively. There's certainly a lot of interest in that.
Next question is, I see a lot of newer systems use one heat pump per floor. Is that now the norm, or is it very situation dependent?
Yeah, it is situation dependent, but I generally quite like that approach if you can get away with it. Um, like if I, here, let me pull up. Let me share this very briefly. I won't do can you see this plan with the loads?
Mhm.
Okay.
Yes.
Um, so this first floor of this example I showed this was kind of wide open. The kitchen, dining, living room, very open, and the envelope was good enough. The loads were modest enough that I would have been one of my recommendations to these people was you could put one ductless head in this first floor, and I would be confident that the the blue, yellow, and purple sections would be comfortable. However, there are these gray and orange sections off to the left, off to the west, which was an addition on over a crawl space, and there's a lot of glass. These are not as well connected to the space. And I said, those, you might need some auxiliary resistance in those spaces in the winter to keep it comfortable. And I can't guarantee you'd be perfectly comfortable in the summer. But open plans like this with a load of, you know, 14,000. This could be a very good application for a single ductless head on this floor. They opted to go ducted because they aesthetics was part of it. They didn't have a good place in this first floor where they thought a ductless head would be okay, would work well and would be aesthetically okay. And they wanted to duct to these Western rooms to get heating and cooling there, which was good. Actually, one of these rooms became a home office during COVID, and they spent a lot of time there. Um, but yeah, this one heat pump for this floor, one heat pump for the second floor. I think that is a great system for a lot of applications. Of course, not every application, because the loads vary, and we do see this. We monitor this a little bit. The lower floor operates more in the winter. Warm air rises. Warm air will rise up to the second floor. That second floor heat pump will have to work less in the winter, and conversely in the summer. The upstairs system would do more cooling. The cooling falls or the warm air rises, and the lower floors need to work less in the summer. And it's also potentially a better humidity control strategy if you run the upper floor system to do your cooling. It'll dry out the whole house more. Maybe again, I haven't seen a lot of good data on that, but I think that can be a very good kind of paradigm, but it does depend on the application.
Okay, thanks. Is there a rule of thumb for square foot of the space and heat pump capacity in tons with good insulation? Must you do a blower door test to determine the size of your heat pump?
So there's no rules of thumb. I really recommend calculating loads. That said, it's not hard to calculate loads. Um, a blower door test is, in that example where my calculated load and the designer's load was so different, the infiltration was a huge piece of that. And that was new construction, so nobody could have gone and do a blower door test on an existing building. If you do have an existing building, an existing home, blower door test would be great because infiltration is such an important piece of that of the design load calculations, the biggest for heating for sure. not for cooling. The biggest drivers for the heating load are getting the design temperature right and getting a reasonable infiltration number. Also, pretty good estimate of window area and performance. On the cooling side, it's solar gains that drive the cooling load and internal gains that drive the cooling load. So those are the most important ones to get right. But no rule of thumb BTUs per square foot. I really recommend doing a load calculation. Good contractors should be able to do that without too much trouble. Maybe it's not something they can do if they come to your house, like walk around your house for half an hour and give you a load calculation. Although there's some new apps that maybe start helping people do that. But I avoid rules of thumb, and really try to do a pretty decent load calculation is what I'd recommend. But it doesn't have to be hard. I can go into a house and have a load calculation within 30 to 60 minutes.
Okay, can you comment or provide a brief overview on thermostats for these systems? What's the minimum needed? What bells and whistles are not really needed or wanted, quite frankly, for less technical people like myself?
Yeah, that's a good topic. Uh, a lot of the ductless systems, almost all really, come with the default handheld remote control. Um, and those can work fine. I recommend a wall-mounted thermostat. That can add $200 or $300 to the cost of the system, which is not, it's $200 or $300. The drawbacks for the handheld remote are a lot of them have a lot of them have suns and snowflakes to indicate heating or cooling, and there's a lot of confusion about which is which. And you can argue valid points both ways, but the sun is heating, the snowflakes cooling. Almost, I think that's universal. That actually confuses a lot of people. And also God, we have these in our office. We have a VRF system in our office, and the sun and the snowflake are so small and they look so similar. I have to go and get my glasses to see if it's the sun or the snowflake. The other thing is those handheld remotes don't sense the room temperature. A lot of people think that they do sense the room temperature. When you use a handheld remote, the temperature is actually sensed up high or down low if you have a floor-mounted heat pump, but it's sensed in the return airstream of the heat pump. So the temperature up by your ceiling at the intake of your heat pump might not be close to the temperature set point you have. So there's a disconnect. Well, I'm always comfortable at 68, but now I'm too cold at 68, so I have to set my remote control up to 72 to be comfortable, and that rubs a lot of people the wrong way. But really, my advice, if you do use the handheld remote, control it so that you're comfortable. Don't pay attention to the number on the remote. If you can, I recommend using the manufacturer-specific controls, be it the handheld remote or their brand of wall-mounted thermostats, because if you try to tie it to a different thermostat, even the smart ones like a Nest or Ecobee or something, the controls of these are, well, it's kind of a black box from my perspective. But for them to run most efficiently, to be able to modulate the speed of the fans and compressors most efficiently, it does that best when it's using their own control system. If you're using a third-party thermostat, and there are adapters, you'll probably have to buy an adapter to connect to the heat pump. It'll lose some of the feedback in the controls to allow the everything to modulate to provide the best comfort and efficiency. There's a lot of debate about setback with heat pumps. Should you set them back? Should you not set them back? My answer is you should control them so that you're comfortable, which may seem like a cop-out. But there's arguments both ways. If you turn one study I saw, the least efficient heat pump in the study was they used their handheld remote as an on-off switch. If they were cold in the winter, they turned it on. Once they were warm enough, they turned it off, on, off, on, off. And of course, the heat pump could not modulate to provide, efficient heating over any kind of time frame. So that had very, very poor efficiency. But if you go away for many hours, and you turn it off, it won't have to run at all, perhaps during those many hours. And if you're more comfortable setting back the temperature at night for sleeping, I say by all means do that. So I try to limit cycling on and off, but primarily control it so that you're comfortable. I
And
don't know.
feeding right into that comment is with heat pumps, it seems like they cannot handle nighttime setback temperatures like furnaces do. What do you recommend for setback temperature ranges?
They can handle them. They when it turns on in the morning, or I'm thinking of heating. So if it's January, so I'm thinking heating. When it turns on in the morning to try to recover, it's going to be screaming pretty fast. The compressor is going to be going really fast. It's going to be trying to put out as much heat as it can to get the temperature up as quickly as possible. That's not its most efficient mode of operation. So its most efficient mode of operation is where it can modulate to adapt to the temperature at part speed. But again, if you're more comfortable sleeping when it's cooler, it can recover. It can zap, it can. Now, a lot of times, like you'll have 100,000 BT per hour furnace or boiler. That can recover a lot more quickly than a 20,000 BTU per hour heat pump heating capacity. So there's a lot of fossil fuel equipment that has a lot more capacity and can recover a lot more quickly. That is an issue. So it might take you a lot longer to recover from setback with a properly sized heat pump. Um, but they can do it.
Okay.
Good
Phil, how do you want
questions.
to do time? We're getting close to 8:30 out of respect for everybody's time. Should I continue to go? You're on mute.
I can stick around for a bit longer if
Yeah, let's
folks
try
want to
to
stick around.
just try to work our way through as many as we can, and we'll
Okay.
see.
Very good. I will. This has a little bit of text to it. I own a new, very tight 2-story, 4-bedroom home in Mid-Coast, Maine that has 32 solar panels and a battery. It's a grid-tied system so that I can use the grid to save my battery and also so I can use my electric credits towards another building I own nearby. It's presently heated with baseboard hot water oil boiler with a summer winter hookup for domestic hot water. I have lots of extra electric credits, so I'm considering installing a hot water heat pump supplement to take the place of the oil boiler. I've been told to set the oil boiler down to 120 degrees and see if the house is comfortable before going with a hot water heat pump, because a hot water heat pump only heats the water to 120 degrees. I thought I could tie in the electric hot water heat pump to the existing baseboard heating system and use the oil boiler as a backup. I'd like to get away from carbon and use my electric credits to heat my house. I'm not concerned with cooling the house because this part of Maine, it doesn't get very hot to begin with. A lot there.
Yeah. I want to make one clarification, and I'm not sure if this asker was thinking this, but when I talked about kind of air to water heat pumps before for uh space heating, there are heat pump water heaters that are for domestic hot water, for showering and washing, um, kind of integrated tanks. It's a big tank, usually goes in basements, the heat pump's on top, and big tank of water. Those will extract heat from the air around it to heat the water. Those uh, generally cannot be used to heat your home because they're extracting heat from your home to heat the water. Um, that's hopefully that's not what somebody was envisioning. I just wanted to make that distinction. The air to water heat pumps that we can use for space conditioning, they have an outdoor unit like the heat pumps that I showed here, where it extracts heat from outdoor air, brings it into the house to heat the home. Um, as to the experiment of seeing if 120-degree water can heat the home, I think that could work. It depends on the system configuration, and your ability to safely and effectively control the temperature of the water going through the pipes. Some boilers don't, depending on the boiler, they don't like return water temperature that is too cold. So you might have to have a primary loop, a secondary loop configuration so that the boiler maintains is happy with the water temperature it has, whereas only 120-degree water is sent out to the baseboards. I don't think it's not a straightforward question to answer. Um, well, yeah, there are Maine especially. There's parts of the country, parts of the Northeast where oil dominates, where there's no natural gas distribution. Heat pumps have taken off because heat pumps can really offer some significant savings over oil usually. And Maine is one of those places. So I know I spend a fair amount of time in Mid-Coast Maine, and I know there are a lot of heat pumps going in and a lot of contractors. Um, I think I actually might be able to dig up a contact for you to get in touch with, but I can't think of it offline. If you want to shoot me an email, I might be able to find a contact in Rockland who I used to work with. That might be a good person to ask about that.
Thank you. Will you talk about groundwater, or can you comment on groundwater or pond water systems to connect to my baseboard system?
Um, I think it's the same, very much similar challenges that I've mentioned a few times, where any heat pumps that produce hot water, that water is going to be at a pretty modest temperature. So 120-ish, where a lot of baseboards are designed to operate at 160 or 180. So it depends on the load of the home. It depends upon the emitters. And to get that to work, you might need to insulate, air seal, reduce the load, and maybe replace the heat emitters.
How do you think we can get to a place where heat pumps are properly sized? If suppliers aren't using criteria, where does a homeowner turn?
That's a good question. Um, Finding a good contractor is, um, God, I'm not sure if I have a great answer for how to find a good contractor. I've worked with a lot of contractors who are fantastic, and I've been dealing with heat pumps for quite a while. And I find that more and more contractors um, are starting to get it. They're starting to trust that the heat pumps can deliver what they're promising. They don't have to hedge and fudge and install way more capacity than is needed just to cover their butts in case people are too cold or too hot. Um, so there's an upward trend as there are more and more contractors who are really knowledgeable and do a good job, and it's awesome working with them. How to identify those contractors? If there are programs, utility programs, or state programs in your region, and there's some qualification metric, that's a start. Um, BPI certification might be a start. At least they're supposed to have kind of a basic knowledge about sizing these systems. Um, but that's a tough question. I'm sorry, I don't have a good answer for that one.
There's a follow-up, another question that says, will you be sharing a list of experienced licensed contractors? Or can you share one?
Um, I know several I'd recommend in the region around me where I work, and some in New York. I don't have a list for a wide swath of the Atlantic, I'm afraid.
I just would maybe throw in two things. One, I would ask if they have if the contractor is BPI certified or if someone on their staff is BPI certified. That's Building Performance Institute. And the other thing is I'd ask them what kind of calculations they're using to size the system. So if they're using a manual J, and if that comes out of their mouths very quickly, you're probably on the right track. If they say, how many square feet, this is how many tons,
Yeah,
walk away.
that's a great point, Phil. Or like for like is another practice. Oh, you got a 4-ton AC, sold, install a 4-ton heat pump.
Yeah, it's another, very common problem.
Yeah. No, very good point. Very good point.
Other than cost, is there any advantage of an air source heat pump over a ground source heat pump?
Mm.
So, a good ground source heat pump should be more efficient than a good air source heat pump. A good air source heat pump, like if you really design, install, and operate it well, and heating COP of 2.5 to 3. A really good ground source system, I think you should have a heating season COP of 3.5 to 4. So it should be more efficient if done well. In my experience, I work in with a lot of efficient buildings, new construction or existing becoming much more efficient. For single family homes, I think the loads of an efficient single family home are so small that they don't necessarily merit the extra cost of a ground source heat pump, because that delta in operating cost is quite modest. It may not justify the upfront cost. However, when we get into bigger and bigger buildings, multifamily buildings or commercial buildings, I think ground source starts to be much, much more appealing for bigger buildings or buildings with bigger loads. So, not an easy answer. Yes, ground source should be more efficient when done well. If you have a small, efficient single family home, I'm not sure it's worth the added cost to do it. So, that's my general take.
How much more efficient is a hot water heat pump versus an on-demand water heater, generally speaking?
So for domestic hot water, it's a different can of worms. The integrated tank heat pumps that extract heat from your basement and put it into the water, they have kind of rated energy factors or COPs of in the threes or maybe even 4. Um, an on-demand water heater, there could be different kinds. There's gas, there's electric. If it's an electric on-demand water heater, it's resistance and it's COP of 1. It's 100% efficient. Uh, so efficiency maybe isn't the question. If operating cost is the root of the question, it really depends on the utility rates. We see if you have cheap natural gas, it's hard for heat pump water heaters to compete, in my experience still. But I'm not sure what exactly what kind of appliances they're asking about specifically.
Could you please note the URL for the training on the last slide again when
Oh
you have a
yeah,
chance?
sure. Yeah, if I put it in the chat, does that work?
Yeah, that's perfect.
Yeah.
That's great.
And then while you're doing that, I'll review the next chat, which is 3 questions. In an older home, will there be a substantial difference between the efficiency of an HSPF 8.5 and a 10 or a 12? We have heard differences between potential installers. So that's question 1.
So HSPF is tricky. I would make sure that it depends where you are geographically. If it's in a colder climate and you want really good performance all winter, um, I really would recommend a inverter-driven heat pump that's really rated in cold climates, and the manufacturer literature will support that cold climate performance. That said, HSPF has a lot of shortcomings when rating variable speed heat pumps. It still makes sense for the single stage heat pumps that you stop working at about 30 degrees, or the two-stage heat pumps, but there are a lot of shortcomings for variable speed heat pumps. So I find HSPF almost useless, unfortunately, when comparing efficiency of systems. However, if you're comparing 8.5 to 12, that's a big enough difference that 12, if they're both good equipment for your climate, variable speed equipment, I suspect that 12 is going to be better. If you're comparing a 10 and 11, I don't know that it would be. But if you're going from jumping from an 8.5 to a 12, that's big. One more thing, HSPF just changed, so the new products are labeled HSPF 2. So, and they're not the same. So make sure you're comparing an HSPF 2. Make sure you're comparing the same value. Don't be comparing an HSPF to an HSPF 2 for different pieces of equipment.
Second question is, why do BTUs not always follow a linear path for some units?
That's a function of just the thermodynamics and how the system. I'm assuming that they're talking about at outdoor air temperature. The capacity goes down as outdoor air temperature drops, and that's not linear. As it gets colder, it's harder. It gets harder and harder to extract energy, and then manufacturers do. They play games with. They take some of the hot refrigerant and re-inject it back onto the intake of the compressor so they can get hotter gas. Um, it has to do with how they design the refrigeration cycle and limitations of the second law of thermodynamics. And beyond that, I can't get you any more detail. You'd have to talk to some of these engineers that work for the manufacturers to get more info on that. But
Okay.
it's harder to extract heat from colder air. It's maybe a very short answer.
Okay, thanks. The last question in this group is, are the new refrigerants SP454 available now? Some say yes, others not yet. Why not wait for new refrigerant with better environmental benefit if you have a functioning unit?
So yeah, the regulations for like all the systems I showed, I think all of them used R410A, which has a global warming potential of over 2,000, almost 2,100. So, a pound of that released in the air it's 2,000 times worse than a pound of CO2 as far as kind of global warming potential. The regulations are shifting. There's so much there's so much in limbo now, but I think it's too late in the game for anything to change on regulations on that front. I believe that next year, in some states, I thought in some states it would be this year, but it got pushed back. I believe next year it will not be legal to install in most jurisdictions, maybe nationwide, not be legal to install R410A refrigerants with a global warming potential above 700 or 800. So 454B, I think, is what was mentioned in the question. That's one of the refrigerants that I think we'll start to see some manufacturers use. The other is just straight R32. Both of them, I think, are going to be better refrigerants. Uh, the issue with the R410A that has such a high global warming potential, it's a blend of refrigerants. So it's a blend of R32 and R25, and that basically is a fire retardant. So R410A it's designated as a non-flammable refrigerant, and so that laws, regulations, codes have required non-flammable refrigerants in a lot of buildings. Those are changing. The new refrigerants we're going to have are designated as slightly flammable or a lower flammability. Um, they can burn, but they're not, explosive. So there are new safety precautions for the equipment. There's new trainings. Installers will have to get new equipment that's rated for these slightly flammable refrigerants. I think that the heat pumps should work just as well, if not better, because the refrigerants will be actually slightly better. It won't be half fire retardant. But as to why install systems now rather than waiting, It's personal choice. I defer to you. If you're building a building now and you want to heat it, I think you use you use what's available. Um, but yeah, waiting a year for systems that have refrigerants with lower GWP potential is a reasonable thing to do, perhaps.
Is there risk with these new systems being less reliable, do you think?
The challenge is that the products aren't available yet. So
Mm.
they won't have the track record, right? I think it's a better refrigerant. I don't think there's going to be dramatic changes in how the systems work, but there are going to be some changes. And the systems won't have the track record. And ideally they'd be available now. You could install them now and they could work out bugs for a couple of years before it's actually required. But that's not the case for most manufacturers. I mean, a lot of manufacturers, you they'll be mandatory in 11 months from now, but you can't see sometimes you can't even see literature on the products. So
Oh.
it's yeah, it's a source of angst in our office for sure. This refrigerant change. So I don't have a great answer. I'm sorry.
Can you quantify the increased efficiency with the new refrigerant?
No, I think it might even be in the noise. It may be a few percent better. Um, maybe, maybe 10%. No, again, I haven't seen much literature on this stuff because the product's not available yet. So it won't be worlds, won't be, certainly less than 10% more efficient, maybe more like 3 or 4% more efficient in practical terms is it's kind of my hunch.
Just another comment about finding a contractor that has the knowledge for a good installation, as their past two installations weren't done following these guidelines that you mentioned. But the next question is, I own an all-electric three-level townhome with a traditional top discharge heat pump. Is it reasonable to replace that with the same, or should I consider multiple split type units?
Um, there are efficient variable speed inverter driven heat pumps that go up to 5 tons in capacity that have the same form factor for the old, you know, on the ground heat pumps that have a top discharge. I It really depends on the application, but I wouldn't argue against that necessarily. But there may also be products you probably would have to change the indoor unit. So um, at least the indoor coil, the system. So it's not like you can take you can't take the just remove the outdoor unit and plug the new unit into the same refrigerant pipes and tie it to your existing air handler and duct system. You would probably need to change at least the coil inside and maybe the whole air handler um, to to work properly and efficiently. But I think the systems can work fine. I think that getting them up above snow is a little more problematic. If you're in a snowy climate, parts of the Mid-Atlantic have to worry about snow more than others. And protecting it from, snow falling and blowing in from the top can be. But there are guards. There are kind of guards designed for these top discharge units to prevent excessive water, snow, ice getting in from the tops. So they they can work fine. A lot of the American manufacturers, especially like Carrier and all the related Carrier, Bryant and I forget all the different names they kind of market under. They have a lot of the kind of conventional looking, top discharge heat pumps, but they are efficient, inverter driven, and really good in cold climates.
There's somebody who lives in Maine that says, what heat pump contractor do you recommend I contact for Midcoast Maine? I'm on the Blue Hill Peninsula in the town of Brooksville. Interested in installing a heat pump hot water heater to take the place of my oil boiler.
A water heater, I'm not, I don't know if I can recommend too many contractors to do an air to water system. But
Well, let's
again,
see,
I might.
interested in installing a heat pump hot water heater to take the place of his oil boiler that currently supplies hot water to their slant fin baseboard hot water system and domestic hot water.
Oh, yeah, that's same issue as before.
Right. So if it's a heat pump water heater, that's a kind of integrated tank heat pump water heater that sits in your basement. That extracts heat from the air in your basement and it heats the water that goes to your showers and your kitchen sink and stuff. You can't take that water and plumb it to your baseboards because then you're sucking heat from your house to then heat your house. It's a zero sum game. They Rob and Peter to pay Paul on that front. So it would have to be a different an air to. I wouldn't term it a heat pump water heater. I would term it an air to water heat pump that can provide heat to your baseboard system. And it's kind of semantics, I realize. Yeah, I don't know. I don't know a specific contractor. I might be able to. There was another question in Midcoast, Maine. You got a lot of Mainers in the Mid-Atlantic.
It's the same one. Same.
Yeah, shoot me an email and my email here. I'll put my email in the chat also, though. I think it was in.
Thanks.
And I think the other final comments are thanks for an excellent presentation, good equipment, good information. And they appreciate the fact that this is recorded. And someone says they wish they had this information 9 years ago when they installed their original system.
I didn't have this information 9 years ago, and we're learning more and more always. So yeah, great questions too. Yeah, thanks for the interest. I hope I didn't get too much in the weeds or over people's heads.
Oh,
But it was,
thank you so much, Rob. It's probably something we could talk about for a week or more.
I do every week.
Yeah. So we appreciate all the comments and everything. And if anybody does have additional questions or so on, we'll try to kind of keep it open. I can't say that we can promise responses on all cases, but if we do see some additional information, we'll post it on the website to share. So we thank everyone for joining us. We thank so much, Rob, for doing this presentation and for sticking around so late to do it. And we'll look forward to seeing everybody on February 25th when we're talking about textiles and fibers. And we have a great month and thanks for joining us. Have a good night.